Okay, so in this video, we're going to build on our knowledge of using implicit differentiation, and we're going to be applying this to finding the derivative of the natural log function. So the natural log function is usually written explicitly as y equals natural log of x. And in order to rewrite this function so that it's written implicitly, and which will allow me to use implicit differentiation, I want to utilize a property of inverses that I've shown right here. So the natural log of x is the inverse function to the exponential function e to the x. And as we can see right here, I've graphed the function e to the x, and here I've graphed the natural log function. And if we notice, it may be hard to see these little coordinates, one property of inverse functions is that for every coordinate x comma y in my function, my inverse function has the reverse coordinate y comma x. And so this is really the property that I'm going to be using to rewrite my function in terms of an implicitly defined function. So if I have y equals e to the x as my function, I can rewrite this, rewrite the inverse of e to the x as x equals e to the y. So this is confusing because we may be used to seeing the inverse function of e to the x as an explicitly defined function. But in this case, I'm rewriting the inverse, which is the natural log of x, as x equals e to the y, and this is implicitly defined. So this is the implicitly defined version, which is equal to the natural log of x. So my goal here is to find the derivative of the natural log of x. I'm just using a different version. It's an equivalent expression. I'm using x equals e to the y to find this derivative. So the process for finding the derivative of x equals e to the y is the same process of implicit differentiation that we've used before. So I'm going to start by taking the derivative with respect to x of both sides. And this is because I'm assuming y is a function of x, even though it is implicitly defined. So I have the derivative with respect to x of x is equal to the derivative with respect to x of e to the y. Now, I know that on the left side, my derivative here will be equal to 1. And before I can take the derivative of e to the y, I'm going to need to rewrite this so that my derivative is in terms of y. So over here, I'll have the derivative with respect to y of e to the y times the derivative with respect to x, times the derivative of y with respect to x. Right? Now, I know if I wanted to double check my work that I could cancel out this dy and dy in the numerator and denominator, and then I'll be left with d over dx, which is how I can confirm that even though my equation looks different, it's still equivalent to the original expression. Okay, so continuing here, I still have 1 on the left side. And now that I've rewritten my derivative in terms of the variable that it's written in, the derivative with respect to y of e to the y is e to the y. And then I'm still left with dy dx. Now, the ultimate step here is going to be rewriting my answer by solving for dy dx. So if I wanted to keep dy dx on this side, I would divide both sides by e to the y. And then I would get 1 over e to the y. Now, usually I'd want to have my answer be left in terms of x. And if you notice here in the very beginning of the equation, we started with the assumption that x is equal to e to the y. So I can actually rewrite this e to the y with x. So if I say substitute in x in for e to the y, I have that the derivative of y with respect to x of the inverse of e to the x is actually equal to 1 over x. Now, remember, the derivative function of e to the x is the natural logarithm. We had just used the implicitly defined version to find the answer. So, in general, thanks to implicit differentiation, we can say that the derivative for the natural log of x is equal to 1 over x.